Hello everyone and welcome to another lecture. Today we will want to talk about functions of operators and in particular matrices. So what does this mean? So far we have only dealt with eigenvalues, operators, eigenvectors, similarity transformation and things like this. But now we are saying there is something called a function of an operator. So let me give you an example first. Let's say logarithm or natural logarithm ln of x. This is a familiar function, right? You can get different kind of x, let's say x, sorry, not 0, 1, 2, 3 and so on, and you can get some values from this logarithm of x. That is, for each and every x there is some value for ln of x. So instead of taking a number, so this is the number, and let me change the color so that you can differentiate. What if we take a function that is taking an argument that is a matrix, where A is a matrix. So these are the type of stuff that we are calling function of matrices. And it might seem a bit weird at first because we are only used to taking functions where our arguments are in general some numbers, either it's real or complex, but they're numbers, right? And we never take any function that the argument comes in the matrix form. So these are the things that we're going to discuss in this video. So let's get started. So the first thing we are going to do is that we are going to take a look at the exponential function, because that's the most easiest one to deal with. So let's say, okay, let me just bold it out a bit. Let's say there is a matrix A and we want to know what is, okay, let me just write it down. And we want to know what is exponential of A. That is, the argument is now a matrix. So let me just write that down. This is a matrix. This is here is a matrix, not a variable, not a number. So the exponential function will now take a matrix as its argument. So recall that if we had a number, say to the power x, we could write the power series, or let me just write it explicitly instead of a sum. We could write it like 1 plus x squared by 2 factorial, x cubed by 3 factorial, and so on, right? So now we ask, can we do something similar for this guy over here? That is, when we are taking the matrix as an argument. The answer is yes. So how do we do that? Let's try to see. The idea is that whenever you write e to the power a, where a is a matrix, you can always expand it by defining a power series expansion, provided it exists. And also note that we are considering this A to be a square matrix, that is a n cross n matrix. So if you do that, the first element will be the identity, that is the analog to this number over here. So instead of a number, now you're getting a matrix, and this is a n cross n identity matrix. The second one will be just A. The third one will be a squared by 2 factorial. Then you will have a cube by 3 factorial, and so on. And the resultant thing that will come from this power series will also be a matrix. So this e to the power a, this whole thing will also be a matrix. So let's now take a explicit example, and for the sake of simplicity I'm going to take a diagonal matrix. And as you already know from the discussions on similarity transformation, you can always go to a basis where the matrix is diagonal. Okay, so let's now take an example out of it. Let's call our A to have the following form. Let's say lambda 1, lambda 2. So this is just a diagonal matrix, and it's a 2 cross 2 matrix, but you can always extend this calculation for n by n. So if you write e to the power a, the first thing you will get is a identity matrix, that is a 2 cross 2 identity matrix. The second thing will be a, the third thing will be a squared, the fourth thing will be a squared by 2 factorial, a cube by 3 factorial, and so on. So let's now break them down, and as you have already know through your homework assignments, that if you have a diagonal matrix, the multiplication for them is very simple. A squared is like this, a cube is like this, and so on. So the final term over here would be an n, so I haven't written that, I just put a dot dot dot. And now in the second line, what you need to do, you need to write things down explicitly. So let's do that and see what happens. Let's just carry on with our definition of this thing and the calculation. So this will be 1 by 2 factorial, and this will be lambda 1 squared, lambda 2 squared, 0, 0. And I am not writing the cubic terms. You can also write that, I'll rather write it later so that you can understand what are the things that are happening. So now this 1 upon factorials will get multiplied with both of these guys. So because this is just a scalar multiplication, right? You guys are already familiar with that. So let me write the whole thing down right now. So, and also we are going to add all the elements with, that is the standard matrix addition. So if you do that, it will be 1 plus lambda 1 plus lambda 1 squared by 2 factorial, lambda 1 cube by 3 factorial, and so on. This term, that is the 1 2 term, this is just 0, and this 0, this 0, this 0, and there will be other zeros over here, they will add up to 0. Here there will be another 0, and the last term will be like 1 plus lambda 2 plus lambda 2 squared 2 factorial, lambda 2 cube by 3 factorial, and so on. Now if you notice that we have actually a very nice result, and that is this pattern over here. Let me just use another color to indicate that. That is over here, this is a exponential pattern, that is this series is just an exponential series of lambda 1. So now we can write this thing as e to the power, okay, this color doesn't seem pretty good on here, so let me just get rid of these things. So now what we have here is that we have this 1 plus lambda 1, lambda 1 square, lambda 1 cube, and similarly for lambda 2 we have this guy over here, and both of them, that is this one will correspond to e to the power lambda 1, and this will correspond to e to the power lambda 2. So our result is very nice, that it's like the matrix just went from a diagonal matrix to another diagonal matrix, but this time the elements got exponentiated, and finally you'll have 0 in the off diagonal terms. So this is how you can actually calculate functions of matrices. But since we are using the Dirac notation, and we promised earlier that it will make our life a lot easier, so what I'm going to do now, I'm going to repeat the same calculation, but this time for n cross n matrix. So imagine that n cross n, writing n cross n, I can take n equals to 200 for example, so it's a 200 by 200 matrix, right? But using the Dirac notation, we can actually generalize this thing pretty easily, and we won't have to write all of these terms explicitly. So let me just demonstrate that. So now let's write another matrix. Let's call it M, and we want to use the Dirac notation, and also we are going to take this to be a diagonal matrix for our convenience. So using the Dirac notation, we can write it as small mi, this, that is in a particular basis I, where these basis vectors are orthonormal to each other. So these are my basis vectors, and this is the n-dimensional space, so you can always write out the sum explicitly. So let's now try to evaluate like this. Again, we will start with the identity matrix, and then we want to write expand this M in terms of those powers, right? So again, it will be M plus M squared by 2 factorial, M cubed by 3 factorial, and so on. But if you recall that the identity operator itself was built out of the basis vectors and something we call the completeness relation. So if you recall it, this was something like this. That is, I'm writing on the side margin over here that it is coming out of it can be built out of the basis vectors using the outer product, and then you sum over all the projections, and this is like a identity matrix. So we are going to use that to our advantage. Let's try to see. So I'm writing I, and I'm not writing explicitly from 1 to n, just write I. The summation is well understood. For M, we can write j, because j is a dummy variable, so it doesn't matter whatever you want to choose. You can choose a, b, c, whatever you want, but because this is a dummy variable, right? And if I had n-dimensional space, this I, j, a, b, whatever I'm going to use, the subscripts, they will always run from 1 to n, sorry, capital N. So let's try to write M now. So let me show you how this thing will work. This will be M of j, j over here, and let me just close this side margin so that we don't get confused. Now you can see there is a square over here. So how can you deal with the squares? M square means writing M 2 times, right? But for the sake of generality, we are going to now choose 2 dummy indices to represent 2 M matrices. Remember, these are dummy indices, so it doesn't matter what you choose them to be, but it's a good practice to distinguish them first so that no one gets confused. So let's call our dummy indices as L and K, and I'm going to stop up to second order. So one of the elements will be M of L, one of them will be M of K, and let's write the L's, that is this one, and the other one as, let's put parentheses as well, and since there is no, okay, let me just get rid of it because I need some space. So after you do this, what you need to do right now is that you have already written for L, right? Now you need to write for K as well. So let me just put another parenthesis to separate them out. So this will be K and K, right? Okay. And similarly for M cube, I'm going to just write the term for your convenience. Let's say you have 3 indices now. So A, B, C. So M of A, M of B, M of C. And without using the parenthesis, I'm just going to write A, B, and C, like this, and so on and so forth. Sorry, this should be cubed. So after this line, we're going to jump down over here. Okay, let me just keep this M cube term so that you guys can understand it well enough. So this will be my cubic term, and there will be a plus, and there will be a 1 by 3 factorial. And since it had a square, so there should be a 1 by 2 factorial, right? Due to the definition over here. So finally, what you're going to do after this line is that keep these i's, then over here keep these j's, and you can actually change them to be I as well. but for this line let's keep them as j, because these are dummy indices. You can always that's why they're dummy, they don't know who they are, so that's why they can change their face, if you know what I mean. And finally you will have this guy over here. So this is where the trick comes, L and K. You can see that I have this guy and another guy like this, and these are orthonormal bases, and we have something like L with K. And if you remember that what bracket algebra told us, that if you have something over like this, let's just mark it with another color, this thing can be actually written as L inner product with K, and this is what, since they are orthonormal, this is just delta LK, right? A component of the identity matrix. So that's what we'll do now. So let me just switch back to black. So we'll have M of L, M of K, and using these two we're going to sandwich them, and we'll have a L over here, and let me write the sandwich explicitly. And similarly over here you can sandwich A and B over here and B and C over here. So the cubic term will be something like the following. So the cubic term will be 1 by 3 factorial, and there will be A, B, C. You will have M of A, M of B, M of C. Finally you will have A. Then it should be a ket. A sandwich B, and there will be a B sandwich C, and there will be another C, and this will give me a delta AB, this will give me a delta BC, and here you'll have a delta LK, right? And when you have a delta LK, you can see that I have summation over both L and K, so I can choose either one and I can sum over the delta functions. And what does this mean? This is canonical delta means that is L and K have to be equal, otherwise we will get zero contribution. So to get the non-zero contribution, the indices have to be the same. So if you consider that, let me just write down the whole thing right now. It's I like this, and the second term instead of J we'll now switch to I, and the reason will be evident very clear. The reason will be clear very soon. Is now MI I, and then you'll have 1 by 2 factorial over here. You'll have, let's say we are summing over L, so this L over here, that is this one, this will be replaced with K, right? And this delta will be gone, and there is another bra of K. So ultimately we'll have something like sum over K, K, K. But K is a dummy index, so I can always switch back to I. So using that idea, I can write I, and I will have MI, that is MI squared. And in case you are not clear why there is MI squared, this is because you have ML and MK. So when you are summing over the L's, you are getting rid of this L thing, right? However, because of the delta, it forces you to write down the non-zero, which forces you to write down the non-zero contributions, and the non-zero contributions will come from only when K and L are equal. So that's why the index in M of K is getting switched to M of L. So you will have a M of L squared, and since L is a dummy index, we are just renaming it to I. So that's why I'm writing MI squared. And similarly for the cubic term we will do the same. So let's now write it down. So this is MI squared, and there is a I of outer product. And for the cubic term, similarly you will find, for here you will have to just eliminate two of the indices. You can either choose it to be A or B, or B or C or C or A, it doesn't matter because all of them are dummy indices. So finally you will have something like this, and the cubic term will be here is that mi cube, and so on. Again, what we can do is that we can see a pattern easily if you just factor out these matrices, because these AMIs, they are scalars. So if you just factor this out, in fact you don't need to factor this out, but just to show you the pattern, I'm going to factor it out, and I can see a pattern like this: mi squared 2 factorial, mi cube 3 factorial, and so on. Again, this is the exponential pattern. So what does this mean? This means that this is just e to the power mi I, right? I mean, sorry, the this is a, yeah, this is it. Yeah, this is exactly it. Now you may wonder, why is this true? So let's take like, how do I know that taking the exponential of a n cross n matrix will result in a that is, an n cross n diagonal matrix will result in a matrix like this. So how does this matrix looks like? The representation is very easy to see. It is similar to the 2 cross 2 example. And you can see that all the elements are actually getting exponentiated. So this is where the power of the Dirac notation lies. We just what we did here at the beginning is that we only tried with the 2 cross 2 thing, but I can give you a 3 cross 3, a 4 cross 4, and in fact when you deal with UN gauge theories, there will be n cross n matrices, something even a paper cannot hold. So that's why this Dirac notation is actually very powerful, because it lets you see immediately. Because recall that we wrote a matrix in general M. Okay, let's not make M, you guys might get confused. So let's take it to be n, and this n had elements like this, right, where we call this is the ith row and the jth column, right? So here this is the same thing. That is, since this is a diagonal matrix, you can see that the row and the column index, those that are coming from these bras and kets, they are the same. So you can readily say that my matrix is still diagonal, and each of these entries are coming with the entry in the initial matrix. So the initial matrix was something like this: m1, m2, mn, right? Each of these elements are now being replaced by the exponential of these elements. That is, this guy in the down is getting transformed into this guy. So this is how you can easily manipulate the exponential of a matrix. And before I conclude, I want to show some general rules. Let's say you have 2 matrices. Okay, let's just take 2 matrices. All right, so let's just take A plus B. This is not equals to e to the power A to the power B. Not always. If A and B commute, only then e to the power A plus B is equals to e to the power A, e to the power B. Otherwise, there will be some extra terms. And hopefully you will learn more about this through your assignments. And the reason there will be more extra terms is because the numbers and the matrices, they are different things. So we have to check every time when we use different things in the same function. So just because this identity over here is true for, e to the power A plus B is equals to e to the power A to the power B is true for numbers when A and B are numbers, but here this A and B are matrices. So these are very subtle things, and hopefully you learn them in some assignments and in the next lectures. So this will be it for today, and always remember that this using Dirac notation is always helpful to evaluate long calculations like this. And the reason, you might ask, why did we choose a diagonal matrix at this point? Because diagonal matrices are particularly simple to manipulate. If you recall from similarity transformations that you can make matrices diagonal, so that's the idea over here. In fact, those S and S inverse 1 won't play any role. So this will be it for today, guys, and thank you.